So good morning, good afternoon, good evening, eCognition users. Hopefully we also have some potential users out there in the audience today. Excuse the slightly delayed start, was finding the right monitor here in my setup. Really excited to be coming to you here before we all kind of spread out and disperse into our diverse vacation destinations this year. We have a really exciting webinar with Dr. Jose Peña, and he's going to be talking to us about their utilization of eCognition and exploring what he calls the coolest algorithms, which I really like this title, exploring the coolest algorithms for complex agricultural goals. So that's the general topic for today. If you don't know me, my name is Keith Peterson. I am the eCognition product manager. Here is a face to go with the beautiful voice on the other side of the microphone today. And before we really jump into this thing, I wanted to review some of the, say, general rules of our webinar today. Everybody is in listen-only mode. That's intentional. But please feel free to interact with us at any time. You can pose your questions to us via the questions dialog. I will be fielding some of these during the webinar, but we also have a block of time post-webinar or post Dr. Jose Peña's presentation that we can certainly use for questions as well. Other notes, the session is being recorded, so don't worry if you have to run away from the computer for a second. Everything's going to be recorded and will be available on eCognition TV in the days to come. So that's our YouTube channel for those of you that are not aware, and you can view the session there as well in rewind and rewatch if you miss things that might fly by you. All right, those are essentially the rules of the session. What are we going to be looking at today? I'm going to start out with just a brief introduction to Trimble eCognition software. Then I'm going to hand over to Dr. Jose Peña to talk about his use of eCognition in the world of precision agriculture. Very fascinating. I'm looking forward to this talk. Like I said, we also have a question and answer period at the end. So make sure you get those questions in maybe earlier. Don't wait until the final bell. You can pose the question at any time. I might save some for the end as well, but make sure to get them in a little earlier than at the last minute. All right. So that being said, just a general introduction to eCognition for those of you that may be new to our software out there in the audience today. The idea is to replace this traditional form of information generation through, say, old digitizing techniques, these manual digitizing techniques through automated processes, okay? And eCognition, Trimble eCognition provides you essentially with a toolbox, a development platform for creating these automated workflows to analyze your image data. That could be optical image data, it could be elevation data in a raster form. We can also support point clouds, as you'll see. And what we're trying to do is extract or transform that geospatial data into information. So we want to create land cover maps, impervious surface maps, tree maps, or we'll see what Dr. Jose Peña is creating in his workflows here. All right, but the goal is to automate the workflow as the data becomes bigger and better out there. A couple of real key concepts in eCognition that are good to understand right up front is what we call data fusion. This is the ability to combine different types of geospatial data sets together within a single project environment in eCognition. So we can not only handle your raster imagery, again, could be an aerial photo, drone photo, satellite photo. We can combine that with any vector data sets that you have of that area, as well as with a point cloud. So you can combine these three different types of data sets, and they can essentially speak to one another within eCognition. You can pull different features, different characteristics of one data set and combine it with characteristics of another data set when creating essentially a class description, and really use the full potential of the information that you have available. Secondly, we have a concept of method fusion. eCognition provides you, like I said, with many different tools, and there is not just a single, say, classification approach, a single classification method that we support within the software, rather many. You can use knowledge-based, where I, as a, say, remote sensing expert, am telling the computer through my rule set, this is what a forest looks like. You can also take an unsupervised classification approach or a supervised classification approach as well. And on top of that, we have tools to use computer vision, so template matching, and of course, deep learning tools within eCognition. But the best part is, for me at least, is that within a rule set, which is your automated workflow in eCognition, I can combine all 5 of these different analysis techniques into one workflow if I needed to. For me, the perfect example is going in, maybe taking a deep learning classification approach and then flowing through into the object-based, knowledge-based approach in, say, refining and really adding some more intelligence to the deep learning. We're seeing a lot of users do that. So again, you can combine all of these workflows or all of these practices together for the best feature extraction that you can possibly get. All right, but that's enough from me. I want to hand over to Dr. Jose Peña. Again, I'm really excited to have Dr. Peña with us today. He is a scientist at the Institute of Agricultural Sciences at CSIC, and I took Spanish a long time ago, but I'm not going to try and pronounce that because I will butcher it, I know. He is also a co-director at the Tech for Agro Research Group, and his group focuses on the development and validation of geospatial technologies and digitization tools for precision agriculture, like I mentioned, as well as integrated pest management. And the aim of the research is really proposing new strategies to optimize crop protection, as well as protection for achieving more sustainable agricultural systems. He has published around 100 scientific and outreach articles. Many of these are supported by the use of remote sensing and the creation of innovative eCognition procedures, which is always wonderful to see. He's been using eCognition since 2007, so that's several more years than I have. Respect there. And what's also nice to see here, he's also been honored to have received several real distinctions from the Society of International Precision Agriculture, as well as the Fulbright Scholarship. So he has that in combination with the PRC Robert Award. And yes, that's enough for me. I'm going to hand it over to the expert. Again, if you have questions that pop up, let me know in the question dialogue. And at this point, Dr. Jose Peña, the floor is yours. I will just pop the screen sharing over to you. And there you are. Wonderful, we see the screen, excellent.
Do you see the screen? Okay.
Yes, looks great.
Okay, thank you, Keith, for this complex introduction and your nice presentation. And thanks to the people who are listening here, who I guess most of them are like me, true eCognition fans. It's therefore a pleasure for me to participate in this eCognition webinar series. For those who frequently use this software, these videos in the eCognition series are a reference and a source of inspiration that allow us to learn about many applications of the object-based image analysis paradigm and to discover new procedures and algorithms that can help us in our image analysis. So in this presentation, I will try to balance between an overview of various of the applications that we use in eCognition for agriculture and give some technical and specific details on the use of some eCognition algorithms, which are very powerful and cool to solve complex analysis. As you told, I've been using eCognition since 2007. For me and my group, research group, is a fundamental tool for our investigation using remote sense imageries. Okay, in all this year, we have been working with various remote sensing platforms, satellite, airborne, UAV, and even with image from ground-based platform. As you know, the choice of this type of image depends on the spatial and temporal scale of our study. Thus, for example, we have used eCognition for studies at the regional scale of agricultural areas with satellite images. As I will show later, eCognition has allowed us to combine various types of imagery quickly and efficiently for these objectives. In a smaller area, but with a tremendous spatial resolution, since 2011, we use eCognition to analyze area image taken with drone for precision agriculture and site-specific with management purposes, as well as for conservation agriculture and tillage mapping. In this presentation, I will focus on 2 case studies on this topic. Also, as you know, eCognition allows us not only to segment 2D image, but also segment point clouds and work with point cloud with 3D information and to analyze both 2D and 3D objects that represent elements such plants and trees. Thus, we also developed eCognition procedure for 3D modeling and quantification of crop variable, plant and tree counting, and for high throughput phenotyping in breeding programs. In this webinar, I will focus on 3 case studies with different characteristics, but in all the cases, we find common highlights. All who work in agriculture know that crops are diverse and variable over time. This nature makes that, from the point of view of image analysis, each scenario is unique at the moment of analysis and different from another moment and from the neighborhood scenario. Therefore, in many occasions, we must combine images of different types or time series to monitor crop change, which make us to work with a high number of images, millions of pixels, and even thousands and thousands of objects that involve a high computational cost. Pixels by density give us only spectral and location information, but are limited, have a limited value. With the OBA paradigm, these pixels become real objects, like we can see here in this scheme, which can give us not only spectral information, but also contextual, position, shape, feature, size information, or how these objects change over time. With this object information, we can develop comprehensive procedures and address robust, efficient automatic analysis. That is the main focus or work with eCognition. It's a milestone to produce this kind of algorithms that can be applied to different scenarios in automatic way. In my opinion, some eCognition algorithms such as image object fusion, find-domain-extrema, working with maps and regions, and the use of looping process or advanced classifications such as random forest trees or convolutional neural network can be combined to analyze these complex agricultural scenarios. So let's see 3 examples in this webinar. First one was developed in a large cropland area in Central California, with the objective to identify the crop types in this area and the assessment of soil management practice and different crop parameters. This analysis is important for agroecological studies, greenhouse gas modeling, or agrarian policy development. In this case, traditional pixel-based analysis of these satellite imageries result usually in inaccurate identification of some crop due to pixel heterogeneity, mixed pixel spectral similarity, or crop pattern variability. The area of study is composed of more than 100 commodities, but major crops were alfalfa, tomato, winter cereal, rice, and all this in this column. So we focus the development of the rule set to this major crop that count around 87% of the total area. The problem here was the high confusion between crop and within crop. We implemented the crop calendar in the analysis in order to distinguish different crop in the area. For instance, here you can see several pictures of the same type of crop in different moments during the phenology evolution of the crop. Here in tomato, we can see in mid-spring are typical emergence of the plants with a high surface of bare soil, a small size of the plant that in the satellite imageries are difficult to see. In mid-spring, we have the full area covered by green vegetation, but with a different evolution according to the decision of the farmer in each field. At the end of the summer, the crop has different management. Sometimes the farmer decide to tillage the land and just remove the crop, or just you can find the crop in a senescent state that is increase the confusion between the same type of crop. In another crop like sunflower, we have a similar evolution, which increase the confusion between these two annual crops. In the case of wheat crop, in mid-spring, the cover crop is green, but depending on the date of the showing of the crop, we can have different color, green, yellows, or a mix of green and color, green and yellow color. In mid-summer, usually we have a senescent state of the crop. In late summer, we usually have bare soil. A problem is with alfalfa that is permanently cover the soil. Okay, they are highly influenced by the cutting schedule. That is between 6 and 10 times a year, which result in high spatial and temporal variability of alfalfa dense canopy. In the case of orchard and vineyard, which are permanent crop as well as alfalfa, usually show green cover from spring to fall and good structure during the dormancy period. Okay, their spectral response may be also affected by bare soil background, depending on the plantation pattern, like the tree size, tree separation, as we can see in this picture. Thus, to analyze this area, we combine in eCognition a full data set of two types of satellite imagery, Aster and MODIS. These are free of charge satellite imageries that can be downloaded for the NASA server and can be used for analyze large areas of vegetation. In this case, we use 6 years of information and combine all the Aster data with for the green, red, and near infrared information have 15 meters of spatial resolution. And also we use the MODIS daily data for the full period, including more than 2,000 images. The Aster was using for field segmentation and classification, and later MODIS information was used for determine the crop calendar date and phenology metrics. Okay, the method that we used was create a eCognition developer rule set and implement a decision trees algorithm using the classification algorithm in eCognition. We analyze the different segmentation parameters in order to create a good segmentation net with the borders and the edge of the different crop in the field. Later, apply the decision tree modeling and use incorporated hierarchical and neighborhood rules in order to improve the classification. This is a fast example of how we perform these algorithms. Here we can see the same area in 3 different dates: mid-spring in the top, midsummer, and late summer. In which we can see, using the combination of red and near infrared, the green values of the vegetation in each of these seasons. Okay, if we point out to one of the seasons, first step was to perform the segmentation of the imageries. For that, we use the multi-resolution segmentation and tested different parameters in order to find the best result that can match the area and the limit of each of the parcels. We use 2 levels of segmentation. In the top level, we apply a scale of 100, and these different parameters that optimize the result. And in the bottom level, we apply a scale, a lower scale, 15 scale, in order to find increase the adjustment of the limit of the object to the real limits of the parcel. After segmentation, we first perform the classification of non-crop in the area, like urban, water bodies, permanent bare soil. This area in which vegetation, the spectral information was permanently associated to non-vegetation with a very low NDVI value, and other land uses like road and length objects. Using this parameter, we selected the non-agricultural area, and after that, we can focus on the classification analysis of the cropland areas. For that, we trained a decision tree algorithm using 300 ground truth parcel, in which we know the crop type, and apply this decision tree algorithm to the full data set of imageries. The result was a classification of the cropland area in the 12 different type of crops that we use for the major crop that we use for the analysis. After that, we merge, using the merge algorithm of eCognition, we merge neighborhood areas that belong to the same crop and improve the classification in this area, in which, due to similarity between the crop, we have some confusion within each crop parcel. For instance, here we see that it's very common to confuse 2 different permanent crops, like walnut or almond, or in other case, alfalfa with another permanent crop in the area. So using similarity and neighborhood rules, we can increase the accuracy of the result by using the neighborhood algorithms in eCognition. So the result of this specific analysis was the creation of cropland classification in several continuous years. The objective was to analyze the area and the position of each of the major crops in the area, as well as to study the cropland rotation in the area that are very important data for the implementation of, for instance, greenhouse gases analysis. Here we can see that with eCognition analyzing the result in 3 different years, we can create the segmentation of the parcel and just only focus to the change in the crop type over time, and detect those parcels with the most common or traditional crop rotation that can give us information about the dynamic of this cropland area. A second objective in this study was to use the output of the Aster segmentation and the output of the cropland classification in order to determine the main crop calendar dates and other phenology metrics using the MODIS time series information. As you know, MODIS has a broad spatial resolution. In most cases, we use eCognition to select the pure pixels that belong to each of the parcels in which we segmented the cropland area using Aster images. For obtain the main parameter of this crop calendar, we use some curve fitting model implemented in the TimeSub software, which can give us the evolution of the MODIS time series over time and determine, for instance, the green up onset and the harvest time in the moment in which NDVI finish. NDVI values is decreasing and just get very low values. Even the full integration of the NDVI series and just the maturity onset or the senescence onset. So the final product that we obtained with these tool set in eCognition was first one product was the crop types in 6 different years and the information, the crop rotation in the different parcels in the area, and the second product was a series of maps with crop calendar dates. This indicate the start of the season and the end of the season. For here we can estimate or calculate the length of the crop season in each of the parcels, as well as some important phenology metric like the increase NDVI increase slope. This reflects the speed in which the crop is increasing the green vegetation, as well as the NDVI decrease slope and the integral of the NDVI values over time. That is a measure, a value of the potential productivity of the crop in each of these parcels. Main conclusion in this case, in this case study from the point of view of eCognition user, is that we could integrate satellite image with different spatial resolution and different area coverage, which was very easy with eCognition. Multi-resolution segmentation currently define the crop field boundary and other land use edge. At this point, I will recommend the eCognition user to see this webinar from Barry Watkins that explain how to improve how to delineate the field boundary in another satellite image like Sentinel-2. I would like to point out that the classification with eCognition based in object-based image analysis classification reported a very high accuracy. By integrating the crop phenology information and some major vegetation indices, for instance, NDVI or NDI7 or other vegetation index for the spectral information reported by the Aster satellite imageries, even in the near infrared, the shortwave infrared information, by using 3 critical seasons: mid-spring, midsummer, and early autumn. I would like to point out that texture feature was very fundamental for the identification of permanent crops, in which the structure of the crop, like the tree pattern or the tree size, are impacted directly in the texture feature of the object in the image. And the eCognition allow integrating curve fitting model-based output for assessing the main crop calendar date and phenology metric at the core parcel scale. I recommend for increase the information about all these procedures, these 2 papers published in Remote Sensing of Environment and Remote Sensing in the last year. Okay, after this case study with satellite, I would like to explain these 2 other case studies using UAV imageries. But please pay attention to the important differences between these 2 kinds of imageries. In the case of after, we have a ground sample distance of 15 meter pixel in the visible near infrared bands, and we can analyze a large area, in this case more than 300,000 hectares, and the number of pixels in this largest extent was 60 million of pixels. This is in contrast with this other type of imagery that we use for precision agriculture purpose, in which UAV image give us a tremendous high spatial resolution in the order of 1 centimeter to 4 centimeter, depending on the flight altitude. If we use a mosaic area of 10 hectares, give us more than 1,000 million of pixels. In the other, between 1,000 million pixels and 60 million pixels. This is more than 10, 20, or 30 times information that in the satellite imageries. So with this information, very high spatial resolution information, we can go to analyze the detail of a tree, or even to see a small plant, like a small seeding plant or a small wheat plant, and even to see the teeny structure of the base soil, in this case in an olive orchard. So this is an advantage to try to analyze these plants and this tree to a high with a high detail, but this is at the same time a problem, because we had to analyze a very large amount of information with a very high computational cost. I will follow with the second case study. In this case, we will use eCognition for site-specific width management in order to discriminate the small wheat plants in early season annual crops. The concept of site-specific width management look for saving herbicide product as well as energy and operation time, and obtain economical and environmental beneficial. The objective is therefore to see the situation or the position of these small weeds in order to create weed maps and export this weed map to machinery that can apply the correct amount of herbicide of other weed control strategies just in the position in the moment needed for the herbicide application. For that, we need to determine the weight emergencies in the early post-emergence crop season. In this case, the algorithms in eCognition had to get several demands. First of one is this algorithm had to be robust enough for any row crops, like in this case wheat, corn, sunflower, that have a different pattern in general, different size, and this algorithm had to be automatically adapted to any of these pattern and row crop structure. Another demand is that the algorithm had to be adaptable to variation in crop and size and crop pattern. Here we can see the same parcel with a separation of 7 days between the first imagery and the second and the first imageries. In this case, the algorithm had to be automatically adapted to this different phenology stage. And the third demand is that the algorithm had to be robust in case, in the most common case of spectral width and crop similarity. In this early season, it's very common that both the widths and the crop has a very similar spectral information, which may be very complicated to use only the spectral information to discriminate between the width and the crop. The main phases in this procedure was here we can see a near infrared image in a maize crop in early season. The first stage to to make a segmentation of the imageries in order to detect the crop rows in the imageries. For that, we apply a multi-resolution segmentation and use the algorithm find-domain-extrema and the feature length width in order to determine this crop row structure. As well, we use the object fusion algorithms that I will explain later with a sample in the imageries and the main direction feature to create these crop rows. After the creation of the crop row, we can separate the vegetation that belong to the crops rows that are classified as crop plants and the vegetation outside the crop row that are classified like weeds. For that, we use assign class algorithms and the feature distance to class in the class to use for the distance the row of the crop. We also apply the supervised classification random trees to analyze the vegetation within the crop row that belong to weeds. That is a very complex objective. And use the algorithm object fusion the area of the object in order to increase the size of the plant until a threshold according to the typical size of the vegetation in that moment of the analysis. After the generation of this width-based wheat crop map, we had to generate a width-based treatment maps. That is the phase 3. In this case, we use the chessboard segmentation algorithms in order to create a quad segmentation with the size of the treatment width and apply the assign class in order to classify these different squares according to the amount of widths below each of the square using the relative area of sub-object algorithm. Finally, these maps are exported to a treatment machinery in order to apply the dose or the amount of herbicide according to the amount of widths in each of these squares. Okay, I will go faster explaining this algorithm. Here is the same imageries. We made the segmentation multi-resolution segmentation, in this case with a scale parameter higher of 140 value, and you see these two values for shape and compactness. After that, we use the crop row orientation, the average crop row orientation of this object in order to determine the crop row orientation of the crop. So we compute a statistical value in which, using these objects in the area, we create a new variable, crop orientation, and calculate the mean or the main direction values of each of these objects. Okay, this information is a typical feature of the object that can give us just the orientation of the crop rows in this specific area. Then we perform a new segmentation to a lower size in order to see the limits of the plants in the remote imageries. In this case, we apply a scale parameter of 10, a similar shape and compactness parameters. And after that, apply the Oxum method to that is automatic threshold algorithm in order to discriminate between vegetation and not vegetation using the NDVI vegetation index. This is automatically calculated in a small region of the area according to the specific spectral information in each of these local area. Okay, after that, we perform the selection of the seed object, that is the higher object, the object in the imagery with a higher length and width values. These usually are in a crop row according to the typical structure of these rows. That is usually with a higher value or length in the ratio with the width of the object. In this case, we apply the find-domain-extrema, that is a nice algorithm in which we using the class filter vegetation in the down level. We select the maximum length and width parameters. This value always correspond to an object that belongs to the crop row in the image. Okay, and we classify this object with a temporal class 1 that we'll use to growth this temporal class following the main direction and the crop orientation that we previously saved in the algorithm. Okay, using this crop row orientation, use the image object fusion. That is a cool algorithm in eCognition, but a few complicated to understand. In this case, we grow this seed object following the main direction according to the neighborhood objects. So this algorithm can select the neighbor objects that maintain the same direction of the crop row that previously we saved in the eCognition algorithm. Okay, we use the best fitting option here that merge the candidate that match the fitting criteria in the best way with the seed object, with this temporal one object, the black object, and configure this combination of value for the target value, set value, and candidate value factor. Okay, in this algorithm, this is the black object, and the algorithm can select between the neighborhood object, can select the object that match the fitting criteria that follow the crop row orientation. Okay, I know that this is a complex algorithm. For that user that want to have more information, I recommend this nice video image object fusion in the webinar in the eCognition TV YouTube channel. After that, we select the next group of objects that belong to the next cross-row orientation using the distance to the object algorithm, and this make a filter of the potential object that can belong to the next cross-row in the images. Next, we perform a loop of this procedure and select the next object with the bigger ratio, length, width, and perform the same operation in this new potential cross-row. Then we perform a loop option in which we select the neighborhood potential object that belong to the cross-row, and following the same procedure, we can determine the full data set of cross-rows in the images. The rest of the variation that don't belong to the cross-row are classified with, and the variation that belong to the cross-row are classified as a crop plant or as wheat plants. So in this moment, we need to distinguish between two parts. If we using this algorithm, we can determine the width between the crop row using a map region looping process. We divide our parcel in different areas, a small area, in which implementing the OPSU criteria, we can determine the plants that belong to the crop row and that are outside the crop rows. Using the vector buffering algorithm, we select this area and classify the vegetation according to the distance to the rows. More complicated is the procedure with the width within the crop row. In this case, we apply two different algorithms, in which case we apply a random forest algorithm and even the convolutional neural network classification using deep learning procedures. Okay, for more information about how to use these algorithms, I recommend to view the fantastic video of Ovidio Silic about the deep learning, UAV, and precision agriculture applications. My conclusion is that accurate cross-row detection is a critical phase that could be addressed by cool eCognition algorithms like find-domain-extrema and object fusion. Weak-row discrimination relies on two phases between the rows using the distance to cross-rows, and within the rows using a random forest algorithm or deep learning algorithms. Customized treatment map can be rapidly created with cheeseboard segmentation algorithms. And for more information, I recommend a different paper that we published in the last year, like this one in 2013, evolution and application to other crops in 2015, the development of the deep learning algorithms in this paper, or the random forest algorithms in this other paper. Okay, very fast due to time limitation. In this third case study, we will apply eCognition for tillage direction map. This is because tillage causes progressive soil movement in the land, and potentially produce severe erosion in sloping farmlands. Due to that, the European Union Good Agricultural and Environmental Conditions recommend the practice of control farming. This is flowing to constant elevation that are perpendicular to the normal flow direction of runoff. The scenario in which can produce a severe potential erosion is which in this area in which land slope is higher than 15%, that we can determine with the use of a slope raster map, and if tillage is performed along a slope aspect. This is in the direction of the slope. For that, we try to use eCognition to analyze UAV imageries in order to determine this tillage mark in the ground. In the last year, we produced the OBIA for tillage procedure to map this tillage direction, these contour farming areas. Here we can see the different direction that the farmer use for tillage some agricultural areas, and we try to determine this direction and which part of the field are matching the contour tillage option or are out of the contour tillage option and therefore produce some potential severe erosion. To explain these algorithms, I will use directly the eCognition environment. Here we can see the area of the analysis. This is a RGB imagery taken with a drone. Here we can see the different operation, different direction of the farmer during the tillage operation, and we try to determine a map that can give us this direction, and then combine this map with the slope of the area and the aspect of the area in order to determine the part of the area with a severe potential for erosion. Okay, here is the rule set in this window, and the different layers that we have in the image. We have the 3 red, green, and blue information, as well as the slope and the aspect of the study area. Okay, the process tree. First, I like to define a phase 0 in which we define the variable in order to adapt the algorithm to any other scenario or any other image resolution. For that, to create the grid that I will show later, we prefer to include a variable in which we indicate in the first step the size of this grid, the large grid that we'll use for a site-specific analysis of the imageries, and after that to perform automatically the segmentation with it adapted to the spatial resolution of the imageries. In the first phase, we make a segmentation using the parcel of our study area. Here we have this different parcel with different pattern and different background and different aspect. Okay, this other field. And first step, we perform the segmentation of this area, and then a segmentation following a grading chessboard segmentation. The objective of this grading is to analyze in different space the small areas of the field in order to incorporate the different aspects according to the background or the color of the imageries in the rule set. So now I performed this phase of segmentation and large grading. I have the solution here. Okay, this is the parcel. and this is the gridding of our segmentation, chessboard segmentation. Then I will apply the procedure for the segmentation of each of the small squares that have different background and have different aspects. Here, for instance, we have a darkness soil and more amount of vegetation. In this other part, we have different background or brightness color. For instance, here we have different structure, different color of the soil. So with this previous segmentation, we can apply the algorithms and to adapt the algorithm to each of these small area, and in this consequently to adapt and to make a robust algorithm. Okay. Another thing is to create in this case I create a looping process in which the same algorithm will be applied in all the different squares here. To follow the result of each of these analyses, we create a variable to loop the number of times that the algorithm is following this loop process. Okay. With the region and maps, we select first we select first one of the chessboard objects here. Then with the region, we select this temporal area, and with copy map, we export this temporal area to a new space in the eCognition algorithm. Okay. So here we can see that okay, here we have this this small area in a small in a new space in our eCognition area. In this way, we reduce the computational time, the computational cost of the algorithm, increase the speed of the application of the algorithm, reducing the computational cost, and we can adapt the result to the to each of the specific characteristic of this small area. Okay. So if we perform next multi-resolution segmentation, we can see here a very small object that can be following the size and the pattern of the tillage marks. The problem here is that these objects, some of them belong to the tillage match, but others can belong to the structure of the trees or even the structure of the shadows in the imagery. So we have to perform an algorithm that can discriminate in a first phase between the soil, the shadow, and the green cover of the canopy of the trees. Okay, for marking shadow, we create a statistical value in we determine the mean value of the brightness in this small area and save this value as brightness mean. Okay, and then apply this value to classify between the darkness and the brightness values in the images. Okay, if I apply this, we can see two different colors. The yellow color, so the pink color belongs to the soil, and the dark color belongs to the shadows and the trees canopy cover. After that, we can focus only to the pink classes and try to determine the the object that belong to the different tillage mark in this small area. Okay, for that, we elongate the object doing a looping process, performing the object fusion algorithm, in which we look for increase the ratio length width in order to create length objects that belong the tillage pattern typical in these scenarios. Okay, here we can see the result. Okay, so we apply this okay, this algorithm, and now we can create very length objects that all of them belong to the different tillage mark in the imageries. Okay, so this is a nice algorithm to create this object with this interesting shape. Okay, after that we perform a merging of the different objects, okay, in order to reduce the number of objects in the imagery. Okay, here I export this small area to a folder using this loop number variable, and using the export classification view using the dynamic export items. This variable loop number was created previously and changed according to the number of loops that we apply this algorithm. Okay, so we can perform this, and just we synchronize these values to the main imageries using the synchronized map algorithm. Okay, as a result, we can see that this is deleted, and we have now here the result of our analysis in the imageries, in the main imageries. So the idea is to perform following a looping process to the full imageries here. Okay, in order to reduce the number of, I will repeat this procedure, okay, 5 times, and we want to see the result in these 5 small grids that can be auto-adaptive to the different background and color in the imagery. Okay. Here we can see the result of our analysis using the export, and how using the export option we can see the result in each of the small grid that following the operation of the rule set. Okay, we are waiting for the number 4. Okay, here. And for instance, using a quantum hits project, we can see, okay, this the result of each of these different analyses using the gridding option. Okay, if the algorithm perform is made in this looping, we can create new analysis and adapt the full algorithm to different situation in our fields. Okay, I perform this for the full area, and here we can see the full result after performing all the study. Okay. So this is the result of our analysis, in which we can see how different tillage marks are computed in the full area. Okay. Okay, after that, we can combine this tillage direction map that we apply in 2 different locations, combined with the land slope aspect raster map, and finally determine the contour and no contour map in our study area. Okay, here we can see that in this location, most of the field number 2 perform a accurate and a correct tillage operation. It's not the same in this other part in this other field. Sorry, in this other location, there is some farmer that perform the tillage operation correctly, and other that doesn't don't do this tillage operation correctly. Okay, to finish the seminar, just a main conclusion from the point of view of eCognition user, the map region procedure serves to adapt our algorithm parameter to local image characteristics like color background, and also reduce the computational cost. Length with tillage mark were detected by adaptive segmentation output with find-domain-extrema object fusion algorithms using the length, the ratio, length width feature. Okay, the tillage direction map and contour tillage maps were created with chessboard segmentation algorithms, integrating slope and abstract raster image. I have not shown this last operation due to time limitation. And finally, for more information, please take a look to this paper that was published maybe 1 or 2 months ago. So sorry for being late. I think I used more than 1 hour, but okay, that's all for my part.
Oh, thank you very much, Dr. Peña. It's extremely interesting. Just to grab the presentation back here and get my screen up. Excellent. For me, some of the things that just jumped out was the perfect example of what I mentioned at the very beginning of this method fusion, through the work that you and your research group have been doing, the combination of supervised knowledge base and then on top of that deep learning, all within one project, is fascinating, and one of the real strengths and one of the aspects I really enjoy about the software. A few questions have come in. The first one I think refers to the first case study that you were showing on the multi-temporal classification of crop types. They wanted to know, did you perform a segmentation for each year, or did you transfer, say, one segmentation across the different periods?
Yes, we perform a segmentation for each year by combining different aster imageries of such year. Okay, so each year combine all the aster imageries, in this case for 3 different seasons: mid-spring, mid-summer, late summer, in which with a parallel study we determined that was the best moment for the discrimination of the different crop in the study area. But we perform a different segmentation in each year, because sometimes it's not common, but sometimes the crop limits, the crop boundaries can change, most in the case of a farmer that decide one year to another to change the type of crop within same field. Okay, sometimes that happen, that decide to divide the field in 2 different crops. For that we have to perform the segmentation according to to the decision of the farmer in each year.
Yep, great. One other question, it's actually also one that I'm frequently asked by users, again, related to the first example of doing multi-temporal approach for the crop classification.
Mm-hmm.
You mentioned that you use you accumulated data over a 6-year period. Is it some users would like to know, is it possible to do that type of a classification with say one acquisition date? So if I just have one image that I receive, is it still possible to do some form of crop type classification?
Okay, we try to study the impacts of the number of imageries for the classification of crops. Okay, obviously, if you try to classify a winter crop using summer imageries, we just only see base soil, okay, or just the cover crop after the harvest of the crop. So it's not possible to discriminate such number of different crop if you don't use unless 2-3 imageries in very different season. Okay, we have another publication in which we try to classify summer crop, only summer crop, combining one imagery in midsummer and another in late summer. If we try to use only one image, the accuracy of the procedure is decreased very much due to the high confusion between similar crop.
Yeah.
So it's not easy to classify crop with less than 3 different imageries.
Oh, that's great. I think it also sort of answers or starts to answer a question that also came in here. A difficult one. You're saying at least 3. This user, if we were to select just if we could select one date, I guess which date would that be? I think I would automatically assume it would be very close to maybe what type of crop you're looking for. That as you demonstrated, different crops go through different phases at different times of the year, and again, I think what we saw here is you'd want to try and collect multiple images to do this analysis, to try not to just base it on one piece, because you're just getting a snapshot of one moment in time during that particular crops or multiple crops evolution.
That is the critical thing, is to analyze the evolution and the phenology of the crop over time. That people who work in agriculture knows that this a crop change drastically from the emergence to the harvest time, change of color, change the structure, change the cover of the ground. In the earlier time, we have a lower amount of pixels with green vegetation. In full development, we have the area totally covering with vegetation, and at the last moment, we have a different color of the vegetation. So you have to integrate all this information in order to have a good accuracy.
Right.
Exactly. Is the only way, I think.
Yep. I would also agree with you, and from what I've seen and read in other areas.
But eCognition can help with this procedure. Okay, you can integrate easily all the information. You can integrate different type of imagery. Now people are using Sentinel. They can use Sentinel-1, Sentinel-2, and also can integrate MODIS with a broad spatial resolution, but give us the evolution of the crop, the evolution of the NDVI information. In eCognition, it's very easy to integrate all the information and just analyze the crop by integrating the information in the algorithm.
Great. Another question came in here. I probably field this one. Is it possible to analyze rooftop type using this? I assume you mean using eCognition. The short answer would be yes. We actually have an interesting customer story that looked at mapping different types of roof types in terms of the roof type material. Within a World Bank project. I believe that's available in the eCognition community. If you go into that in our eCognition community, I'll show you all the resources in just a moment. You should find that piece there. Whether they did that with just purely RGB imagery or not, I would have to look back to the article. Another question came in here, and this will be the last one we field before starting to wind down the session, is can we use this method to remove weeds from sugarcane when sugarcane are 3 feet tall? So they're referring to the second case study that you showed, where you were identifying weeds between and within crop rows. Do you think that's possible in a sugarcane environment when the plant has already reached that 3 feet or 1 meter height?
Yes, using the pattern of the sugarcane that usually follows rows, and you can see the position of these plants, of the sugarcane plants, and just trying to apply a similar approach. Just determine the pattern of the crop, and just using the distance to the crop algorithms, try to discriminate the width between the rows. And in order to discriminate the width within the row are more complicated, but I recommend the convolutional neural network algorithm, for instance. For that, you have to train the algorithm, and you can use the width information between the rows to automatically select the training data set, because maybe the spectra and the other feature of the plant, or the wheat plant within the rows will be similar to the neighborhood widths, because are the same width with a different location. So we apply this idea of training the data set with the width between the rows to analyze the width and to discriminate the width within the rows. So that's a nice approach to solve this kind of complex objectives.
Great, excellent. Oh, that, I think we'll wrap up the questions there. If you do have more questions that come up later, I'll show you where you can let us know about those. One great piece was that Dr. Jose Peña already mentioned a number of our great eCognition resources that are out there. But if you have questions in regards to this webinar, you can also go into our eCognition community. You can start discussions there. You can reference some of the tutorials, as I mentioned, these customer stories about the rooftops. You can find that in the eCognition community. We're active in social media. Join our LinkedIn group, for example, and you can stay up to date and also interact with a number of eCognition users. We have eCognition TV. This is our YouTube channel. That we've called that out a number of times. We have multiple different types of material available there. Some of the deconstructed videos that were pointed out there. There's one there on the image object fusion. Great place to start, where we really start to take apart the software and explain how individual algorithms work. That will hopefully make it easier for you to implement them. We have eCognition support, so always you feel free. You can reach out to our support team with your questions, and they will get you an answer. There's the eCognition blog. I've featured some work from Dr. Jose Peña and his team there as well, and it was great having to see that come full circle with the webinar today. But you can also find a number of applications reviewed there. Always take a look at our documentation, it's very helpful. And yeah, obviously webinars, we have a whole host of webinar topics that we've covered in the past. Again, you can find them all very easily on eCognition TV. And finally, although it's been a little difficult during this COVID time period, we have training courses. You'll see a whole bunch of training available online. Some of them, quite a few of them actually, are free training where you can get access to material there as well. And hopefully we'll be on the road again doing on-site trainings soon. But again, if you want to find those online courses, learn.trimble.com, search for eCognition, and you will find those. And that wraps it up for me. I apologize if we kept some of you a little late, but hey, it was so interesting. I didn't want to interrupt and cut things short. So hopefully you will just forgive me for that. I want to thank Dr. Jose Peña for taking the time to present today. Fascinating projects, and I really look forward to seeing more of your research and results in the future. That being said, to everybody, thank you for attending today. Again, the session will be up online soon as soon as we get it processed, and we hope to see you next time. Have a great rest of your day, great rest of the week, and enjoy. Take care.